So, we begin with lecture 12 of the solar photovoltaics course. So, just a brief recap. So, in the last lecture we learnt about semiconductor resistivity, for probe measurement, to measure the resistivity, and then concepts related to semiconductor band diagram. Okay. So, basically what is the direction in which energy changes, in what sense the sign of energy is important, how does the band bending occur, and how do you plot electric field, potential and charge density in a semiconductor. This will come useful when you learn about the junctions. Now, next topic that we take up is the carrier diffusion. So far we have seen carrier drift, which is the movement of charges under electric field. This is movement of charges under a concentration gradient by and large. Okay. So, diffusion is basically a physical process in which carriers move from one place to another, and as a result they need to have thermal energy. So, at T greater than 0 Kelvin, every carrier has some thermal energy. So, thermal energy is kT, is the thermal energy, and if you take the so if you have a species like these, and generally, well, you won't have such a ordered state. So, let me just draw. So, if you have a situation like this, okay, where let us say on this side you have more carriers than on this side. Okay. So, carriers would like to move in this direction overall, but since diffusion is a random process, there could be overall carrier can move in this direction as well as in this direction, right, but there is a net flux in one direction because of concentration gradient. Now, since any species at a given location has probability of moving to either right or left, so we say that the thermal energy which is available to a species to move in one direction is kT by 2. So, it is kT by 2 is the additional thermal energy which drives the diffusion process. Okay. So, of course, at T is equal to 0 K, you have no diffusion because you have no thermal energy available. It is only at energies higher than 0 Kelvin you have thermal and diffusion taking place. So, the scenario is something like this. Let us say you have a picture like this, in which, so very simplified diagram of how a concentration gradient may look like. So, these are let us say the positive charges. Okay. So, we have net concentration gradient in this direction, all right. Let us say this is x. So, in this direction we have what we call as J P diff. Okay. Similarly, you might have a scenario in which you may have concentration gradient like this. So, these are let us say negative charges. So, in this case the movement will also be same. So, movement of carriers will also be in this direction. This is the direction of movement, and the same will be the direction of current, all right. In this case the movement will happen in this direction. This is for negative carriers. If this is x, the distance is scale. So, you have a concentration gradient like this, the diffusion will take place in this direction, but the current will be measured in this direction. So, this will be Jn diff. You can also write it as Jp diff and Jn diff. Okay. Now, of course, these are taken as vectors also. So, you can write them in vectorial form. We will in fact eventually write them in vectorial form. All right. So basically we have Jp diff as minus of q. Now, we know that from the Fick's law, the flux J is proportional to dC by dx, that is the concentration gradient, and we write this as J is equal to minus of d into dC by dx. All right. This is the Fick's first law, which, and this minus sign is because of concentration gradient, because charges are moving from higher concentration to lower concentration regions. So, that is why you have this negative sign. Now, if you now correlate the flux of charges essentially is equal to, so let me just write this expression in a slightly different form. So, for positive charges it would be minus of dp, or you can dp into d dx, that charge concentration gradient, basically gradient of charge concentration, and this is nothing but you can say q, this is the total charge, right, q multiplied by nh, right. Okay. So, this will be minus of q dp into dnh divided by dx. Okay. You can also write, so we will have to make some simplified language later on. We will have to later we will write nh as p and we will write ne as n. We will write that later on, because when we write the equations it becomes very simple, but that we will do later. Okay, later. So, this is the diffusion current for hole. J diff is equal to minus of dp minus of q into dp into dnh over dx. Similarly, Jn diff, now since Jn diff is in the opposite direction as to the concentration gradient, that is the flux of carriers, the sign is opposite. So, essentially the sign is now minus of minus q dn dne by dx. So, this becomes q into dn dne by dx. You can write them in more general form, where d, alright. So, dn is diffusivity of electrons. So, dp is diffusivity of holes. The units of these are in centimeter square per second, whereas the units of nh and ne are in per meter cube or centimeter cube. So, in this case we will take per centimeter cube. All right. So, if you look at the flux now, the current will be so you have q in coulomb into centimeter square per second into, you have n as per centimeter cube, and this will be centimeter. So, if you look at the units now, this is coulomb per centimeter square per second. So, essentially it is coulomb per second is ampere, ampere per centimeter square. So, basically the number of amperes passing through per unit area. All right. So many charges, so much charge in coulomb passing through an unit area per unit time. Okay. So, this is what the flux is basically, and this is nothing but current density, because current density is always represented in ampere per centimeter square or ampere per meter square, whereas current is given in ampere only. Okay. So, essentially this is what it means, number of charges passing through per unit area per unit time. So, now having looked at the diffusion current, what is total current? Total current is Jp. Okay, let me, before we write this, let us just write the general form of these equations. The general form of these equations general form of diffusion current you can write this as, so Jp diff can be written as minus of q dp into del of p, okay, and Jn diff can be written as minus plus of q dn into del of n. So, instead of writing del of nh, I have now shifted it to del of. So, essentially what we have done is nh is represented as p and ne is represented as n. Okay. So, they'll look a little bit more simpler later on. Okay. So, this is what these general expressions for diffusion currents are. So, the total current now so Jp total is equal to Jp drift plus Jp diffusion, and this is basically equal to Q. So, I replace NH by P into mu P into E, remember that. Okay. So, this is the total amount of charge per unit volume, this is the mobility and this is the electric field, plus what is Jp diff? It will be minus of Q dp into del of p, alright. So, this becomes Q p mu p E minus of Q dp del of p. Similarly, for electrons, Jn total will be equal to, for electrons you can take the charge as minus of Q n mu n E plus Q into dn del of n. Okay. So, this we have taken this we have now replaced Ne and Nh by P into Q, right. So, here we have replaced this as N into Q. So, essentially and since for electron its charge is negative, so we have taken it as a negative. Okay. So, J total for a given semiconductor will be equal to J P total plus J N total, alright. So, this is the, you can say J P and this is J N. These are three expressions which are important later on. You can see that for holes the diffusion current is negative in sign, it will become because you have this for holes, the holes move in the same direction and current is calculated in the same direction, whereas for electrons the current is measured in the opposite direction as compared to the flow of electrons, alright. So, these are the two expressions that are important for you to understand. So far what we have seen in a semiconductor, you have carriers move under the influence of electric field, or they move under the influence of concentration gradient. So this is about the movement of carrier action. There are few more things which happen in semiconductor which are important from the perspective of solar photovoltaics, is generation of carriers and loss of carriers. Okay. So this is called as, so you can say this is semiconductor X. So here you have electrons, you have holes, so they move, but now the question is, do they move with the same concentration, or do they get lost at different places, or do they get increased at under various conditions? So for example, what will happen when you shine light on semiconductor? You expect that carrier concentration will increase if light has sufficient energy to excite more carriers. Or what will happen if you have impurities, if you have defects in the semiconductors, the carriers might face a grain boundary, carrier might face a trap or something like that, they will get lost. So this process, in addition to drift and diffusion, which is about the carrier action, you have two more processes. So they will determine the net flux, but the flux is also affected by two more processes, which is called as recombination and generation. So it is these four processes together which will generate the net change in carrier concentration as a function of time or distance in a semiconductor. Okay. So let us see what these things are. So we now focus our attention on recombination first. So we will talk about the generation in the second half. Let us first look at the recombination. So recombination, as the name itself suggests, in a semiconductor, charges can recombine, which means electrons and holes being equal and opposite charges to each other, they have a tendency to recombine. So the first mechanism that is operative in semiconductor is called as band to band recombination. What happens in this case? You have a hole, you have electron. Okay. This electron may move. So this is conduction band. So this is EC, this is EV. So here you have conduction band, here you have valence band. The electron may relax from conduction to valence band to recombine with the hole. In the process, it will lead to a photon, okay, of energy E. So this is band to band recombination, which is called as radiative recombination. So it has emission of a radiation of energy h nu corresponding to the energy which is released. Another process which is called as RG recombination, or it is called as recombination, generation recombination, or you can say the trap assisted recombination. What happens in this case is you have a band. So you have so this is EC, this is EV. You have a trap somewhere sitting in between. So this is a mid gap impurity level. So you have an impurity which is neither close to conduction band nor close to valence band. It is not able to ionize itself. What happens in this case? You have an electron sitting here, you have a hole sitting here, sorry. The electron and hole may reach here and they may recombine, and this kind of recombination is called as trap assisted recombination. And this is a very common mode of recombination because impurities are present in. So this could be impurity, it could be defect, something like that. It could be, for example, vacancies, it could be dislocations, all of them they create defects at the mid level. So every defect has certain energy level. So when you map that energy with respect to conduction and valence band, it is often in the mid gap position, and that helps in carrier recombination. So electron may come here, hole may go there, recombine. Alternatively, electron may go here first, then it may go there first, and then it will combine with hole, leading to recombination. Okay. So this leads to generally release of heat or phonons. So this is called as non-radiative recombination. Okay. Okay. And the third common mode is recombination via shallow levels. In this case, what happens is that you have band EC, EV, you have trap levels which are sitting close to conduction or valence band edge. You might have some things here. Okay, these are shallow levels. So shallow means they are closer to conduction and valence band edge. So you have electrons sitting here, you have holes sitting there. So what might happen is that you have electron coming here and hole going there, or you might have electron coming here, hole going there. Okay. So it happens via shallow levels. So again you have, in this case you may have some radiation coming out of appropriate, because this energy release is quite large. So as a result it's possible to have this in a radiative manner. So possible for radiative emission to occur. So this is via trap levels. So these are the three main causes of recombination. However, the most common cause in semiconductor is this trap assisted recombination, where impurity and defects they lead to recombination in semiconductors. And of course, band to band recombination is also very common. This is especially true when your carrier density becomes very large. When your carrier density becomes very large, then the energy also becomes very high. When the energies become very high, so more the carriers are created, more the carriers recombine thermally. So this is basically thermal recombination. They just come to valence band to recombine because carrier concentration is very high. So this is the recombination process that happens in semiconductors, and you can also have other recombination processes such as recombination via excitons, you can have Auger recombination. So there are various recombination processes which are there. We can't get into details of everything, but if you want to read more about recombination, I would recommend you to go through Robert Peire, Advanced Semiconductor, Fundamentals, Volume 6. Okay. So go to this book. So this is about recombination. The main methods for recombination are band to band recombination and trap assisted recombination. There are other methods as well, but they are less common as compared to the first two. And then we have generation. So first we just look at the processes and then we quantify them. Okay. So generation happens first because of thermal generation. So you have EC, EV for a band diagram of semiconductor. So electron here gets excited, creating an electron, leaving a hole. Okay, so this is thermal excitation, thermal or light assisted generation. This is what happens in solar cells. You have a radiation of energy. So basically energy E thermal or E light is greater than Eg. Okay, so this is the band gap. You need to overcome this energy to thermally excite or photo excite the carriers. So what it requires is that energy of radiation or energy of the heat, the thermal energy has to be larger than the band gap. So this is called as band to band generation. Very common mode of generation in semiconductors. Second generation mechanism is, which is because of defects. So you have EC, you have EV, you have trap somewhere here. So you provide some thermal energy. This thermal energy leads to creation of carriers in this fashion, so that you create a, so electron from here, it first goes to this stage, then it goes to this stage. So energy is provided in parts, you do not get like all of the energy in at once. So this is called as RG center generation. Not very common, but is possible. And then of course you can have photo emission from band gap centers and impact ionization that can also cause, but these are two major modes of generation. The other modes are photo emission from band gap centers, such as traps, okay, energy levels, and then you can have carrier impact ionization assisted. Carrier generation. So again, if you want to read more about these, go to the same book which I recommended, Advanced Semiconductor Fundamentals by Pierre. So these are the main methods of recombination and generation. How do we quantify them? So for quantifying them, we have what we called as RG statistics. Which give us generalized rate relations, because these things, and bring some time dependence into picture. So basically we say del n by del t Rg is time rate of change in electron concentration due to both Rg center. Okay. So it's negative if electrons are lost, and it's positive if electrons are created. Similarly, due to Rg centers, not both, but Rg centers. And then we have del P by del T Rg, which is time rate of change, same in hole concentration due to Rg center. Again, this is positive if holes are created and negative if holes are lost, and this includes both capture and emission. Okay. So negative means captured, emission means it's positive. So we will quantify this, we will couple these with the terms that we have seen from drift and diffusion, and then come to the final equations of rate of change of carrier concentration in semiconductors. So we will finish here today. What we have learned is about recombination, generation, and some diffusion aspects in semiconductors, and we will take it up further in the next class. Okay, thank you.